So first of all, thanks for inviting me to this workshop. It's really very stimulating, and I'm learning a lot in terms of language and approaches of indeed somewhat different community. Although the subject that I'm touching up today is actually probably closer to the audience than to myself, but nevertheless, I'll try. So, actually, the problem of interplay between magnetism and superconductivity is not a new one, but it got some boost over last few years because of the prospects of building some non-trivial topological states of matter out of very conventional components, which are magnetic ions and superconductors. So what I would like to do first is that just to give a few minutes of motivation to study this interplay. And then I'll discuss in quite detail the interaction structure induced by a single magnetic ion embedded into a superconductor. That will bring the notion of so-called Shiba states, or U-Shiba or Sinov states. And that's kind of a more or less textbook thing. And then I proceed to considering chain of atoms, which is a bit more advanced. And that will give rise to this question about the induced P-wave superconductivity along a chain, and possibility of having this non-trivial zero energy states, Majorana states, at the ends of the chain. So that's the plan. I hope that we'll have enough time, and please interrupt, because I mean, it doesn't matter whether I'll cover everything or stop somewhere in between the parts. So first of all, just about the idea of topological non-trivial states. At some point, people realized that actually you can have a non-trivial state in quite ordinary material. And the simplest object to consider, simplest to date, is a quantum wire. So it's one-dimensional electrons with spin orbit interaction. So consider just first single electron with the dispersion p squared over 2m. And then if there's on top of it spin orbit interaction of the simplest form, then basically it adds a term like this one, proportional to the spin of the electron. And this term kind of shifts the parabolic spectrum depending on the orientation of the spin. So for sigma x equals +1, it's this blue parabola, and for sigma x equals -1, it's red parabola. So two parabolas are shifted. So instead of single parabola, which is blue-red, there are two parabolas, one blue and one red, which intersect at k equals 0. Now, if we put such a wire in contact with superconductor, the simplest thing that happens is that the wire gets proximitized. So there are pairs of electrons that can tunnel into superconductor and out. So it's kind of Andreev reflection process. And what happens is that we have to take two states which are coupled by time reversal transformation. So here, p sigma and minus p minus sigma are two states that correspond to time reversal transformation, and these two states can be coupled to a superconductor. So from S-wave super, we can tunnel a pair out into wire, or take a pair of time reversal conjugate states in a wire and tunnel into the super. So if we have no other ingredients in the system, then this proximity-induced superconductivity corresponds to opening a gap around the Fermi level, right? So there is a gap. And this description is good as long as we look at energy states well below the gap in the superconductor that induces superconductivity, okay? So as you see, this Hamiltonian allows electron pairs to tunnel from a wire into the super, okay? But it's not true hybridization of states that was discussed again over these 2 days that we have been here. So single electrons cannot go from a wire into superconductor. It's an artificial model, I would say, but it's good enough as long as the induced gap, delta S, is much smaller than the gap in superconductor. Okay, then basically there are no states to tunnel into for single particles, but pairs do tunnel because they can end up in the condensate. Okay, so now if you put one more ingredient, namely magnetic field, with direction of the field non-collinear with x. Okay, so for example in y direction, then in the absence of superconductivity, this field will cause polarization along y direction or precession around y direction, and this is a Hamiltonian that is kind of fighting with this one, so they're not commuting. And what happens as a result is that it does affect the gap. Now, as you see, this is homogeneous field as I put here, so only the states with the same momentum are coupled. So therefore, these states are not affected, finite p, but these pairs of states with p equals 0 are affected by this interaction with magnetic field, the Riemann term. And as a result, when I crank up the field, the gap at p equals 0 first closes, and upon further increase of magnetic field, the gap reopens, but it's kind of Riemann-like gap, right? So it's having polarization along y direction up and down, having different energies. So this gap actually does correspond. There is still proximity effect, so it's still a superconductor, but it's of a p-type. We will see it later. It's p-wave superconductor, basically. So once again, at b larger than delta s, gap reopens, but the nature of states at p equals 0 here is different from the conventional s-wave Cooper pairs. So that's basically three ingredients, right? So the spin-orbit interaction, proximity, and Riemann. It was realized quite soon that actually one can get rid of one of the components, namely one can do away the spin-orbit interaction. And for that, we may consider just the wire without spin-orbit, but magnetic field then must be not uniform, but rather forming a helix in some direction, well, in direction of the wire. Then one can do a gauge transformation, basically linear transformation, very similar, I would say identical to what Alex Tarikh had yesterday, that moves you to the basis that kind of has momentum boost with momentum kh, the helix pitch. And after this transformation, we'll get back to the Hamiltonian that I have just had on the previous slide. So it will be kind of spin-orbit-like Hamiltonian with the spin-orbit constant, quote unquote, equal to the pitch of the helix, and magnetic field in this new frame will be just homogeneous field. So once again, magnetic field does break time reversal in either case, and if it's an addition in homogeneous in space and forms a helix, then the spin-orbit plus homogeneous field is the same as having helix and no spin-orbit. So now if in addition we put proximity effect into picture, we'll get back to the same story with possibility of forming p-wave states at k equals 0. And this analogy was understood quite early by various groups. It's Basel, Leiden, and Denmark, Copenhagen. And the goal is that having this non-trivial p-wave superconductor in one part of the system, for example, if I can by some magic vary proximity effect, delta or vary magnetic field, in one part of system one can have a p-type superconductivity, another part of system is s-type, and the interface is supposed to carry this non-trivial zero energy states. So now next level of models was introduced by Princeton group, and I will not speak about this particular work at any length because Sevan speaks right after me. So the idea is basically was just to take exact copy of this wire papers and replace the external magnetic field by the interaction, exchange interaction with local moments of magnetic ions embedded into superconductor. So basically, instead of magnetic field, there is this term that acts like magnetic field. And if the spins of atoms are for some reason helically arranged, then this is this helical field that even in the absence of spin-orbit interaction would produce non-trivial state. And this is basically the essence of this proposal. Then we just can use an analogy with proximatized nanowires and get all the same results with prediction of Majorana states at the end of the chain. And again, it was done by a number of groups. So I will not discuss in detail why actually one may expect helical arrangement of spins. First of all, a number of people here understand it better than me. Second, I'm not sure that it's true. So, the only comment that I'm sure that, well, I think that I know maybe a bit more detail than others, is that superconductivity doesn't affect much the magnetic structure of embedded ions. We know that in normal metals, magnetic ions interact by RKKY, Ruderman, Kittel, Kasue, Yasuda interaction. Basically, it's exchange of two magnetic ions by spin waves, if you wish, or itinerant electrons, spins. And it's oscillating in space, right? So it oscillates with the pitch given by half of the Fermi wavelengths. Now, superconductivity does affect this interaction, but only a little bit. At larger distances, actually, the oscillatory interaction is replaced by just antiferromagnetic interaction. And this is a consequence of having a gap in spectrum. And I will not dwell on it. But the point is that this crossover from RKKY to antiferromagnetic interaction happens at relatively large distances. So the characteristic distance at which it happens in units of Fermi wavelengths is square root of Fermi energy divided by gap. So typically it's, well, 1 eV over maybe 1 MeV, best case scenario. So this is, I don't know, it's 1/30th or something, or 10 to minus 2. And at these distances, there is so weak interaction between ions anyway that it's not interesting. So basically, if the chain is relatively dense, then you can disregard the effect of superconductivity on the indirect exchange between ions. So whatever you know for normal metals carries over to superconductors. And again, in simple-minded picture, one would just maximize the Fourier component. Well, look at maximal Fourier component of RKKY interaction, and that will determine the period of helical structure of ions in a chain. And then the sense will be dependent on spin-orbit interaction. Something should break the degeneracy between left-handed and right-handed spirals. But as we know, there are other things that are probably more important, as the Zalchevsky-Marie interaction and also single-ion anisotropy. And this is a subject of big investigations in theory and experiment. The only thing that I would like to mention is that there were some experiments that could be interpreted as having a helical arrangement of magnetic ions along a chain with period that has little to do actually with Fermi wavelengths and apparently is controlled by DM. But the matter of fact is that in the experiment that probably we'll discuss later, the chain of magnetic ions, iron atoms, actually is ferromagnetic. Okay, and that was checked by spin-polarized tunneling. And probably that's because the distance between ions is quite small, and there is direct coupling between ions as well as the indirect one. So it's not a big deal yet, because as we discussed, if there is spin-orbit interaction, then having homogeneous magnetic field is not so bad. Now, lead is a heavy element, so spin-orbit, atomic spin-orbit is strong. And on top of that, of course, in the bulk, lead as any metal, or essentially any metal, the elementary cell has inversion symmetry, so spin orbit is kind of cancelled. But at the surface, the inversion is broken. So there is a Rashba type spin orbit interaction at the surface. So it's not that bad to have ferromagnetic ordering. That doesn't kill the idea of an interior topological state. Now, what was found in the experiment that there is something resembling a gap, and again, probably data has improved since what was published. But if you have a loving eye, you can believe that there is a gap, which is narrow compared to the gap in the lead. And the spectra are different, tunneling spectra are different in the middle of the wire and at the end. And there is some state, apparently, that is localized near the end, and it's really localized at the end. The range over which the tunneling spectrum is very different from the bulk is very small. So this size of the red spot is much shorter than the coherence length in the lead. So, and that actually caused some consternation in the community, because we know that the gap and the coherence lengths are inversely proportional to each other, right? So the smaller the gap, the larger the psi, and the other way around. And therefore, having a narrow gap, more narrow than the gap in lead, and at the same time, the coherence length, which is basically defining the edge state on the chain, much shorter than the host material coherence length, is a bit strange. So actually, to understand, I believe that it's understandable, it can be understood, but for that one has really to go beyond the simplest model where one treats the states that form one-dimensional superconductor and the host material separately. So one has to go beyond this model where there is just proximity term put by hand and look at a model where the electrons, all electrons, are looked at in the same footing. And that's basically what we did in a few papers with a group of Felix van Oppen. So I mean, to kind of, as a shameless advertising, I would say that there was indeed, well, statements from strong to moderate about this apparent inconsistency. So cannot be reconciled, and here is not yet fully understood. And it was about a year ago. But I think actually that there is quite simple explanation that does reconcile the narrowness, the gap being narrow and the localization length being short. So for that, I have to go back and start with just, yep. Sorry. Yeah, I'm sorry.
How do we know that it's a B-wave?
How do we know that experimentally we don't? I don't know it. Okay, so now, so experimentally it's not known, I believe. Now, from theory point of view, why I would be surprised if it's not p-wave, I can tell, because you have, you'll see it's on each side you have a state only for electron with a given spin, with one direction of the spin. Okay, so you cannot put electrons on the same side. So it must be some coupling that is allowing the Cooper pair wave function to be 0 at equal coordinates. So that's why probably it's not S-wave. That's as far as I can go. But experimentally, I don't think there is any clear manifestation of p-waveness. Yeah, so any questions, just raise your hand, shout. So let's go back to a magnetic ion in normal metal. So the kind of model of choice is Anderson impurity model, and the idea is that we have a strong on-site Coulomb repulsion. So if we embed an ion into a Fermi C, then the energy for the additional electron is still larger than the Fermi energy, so the atom retains its magnetic structure at least as long as there is no hybridization between the localized electrons on the shell and the conduction electrons. Now we turn on the hybridization. The level broadens up. And what Anderson did, he analyzed the phase diagram of the system just in the mean field approximation. So in this mean field, basically the important variable was the retained magnetic moment on the ion. And here's the phase diagram. So it just tells that as long as the overlap, as the level width gamma is small compared to the Coulomb repulsion on side, the atom remains magnetic. So in the further discussion, I will look at the case when the level width is small. So this resonance is narrow compared to the distance to the Fermi level. Okay, so gamma is less than u, and that is important. Now, for pedagogical reasons, I also will consider a situation when this distance, so the distance for electron-like excitation, is smaller than this distance, which is the distance for the hole-like excitation. So it costs more to take out an electron than put in, but it's just for convenience. So we are somewhere in this region of the diagram. So on a very simple level, what superconductivity adds to the picture? So let's look at very unrealistic, simplistic picture. When gamma, the level width, is much smaller than delta. It never happens, but suppose it's true. And on top of that, let's look at the situation when this level is just above the Fermi level. Okay, so let's assume that the position of the level is within the sliver of states that are gapped out by superconductivity. Okay, so before superconductivity, there were states in the bulk that this level could overlap with. So there was a width of level because of tunneling. Now we gap this region of energy spectrum. So there are no states to hybridize with. And therefore, there is no level width. There is a level, but no width. Okay, so level remains discrete. So that's the first qualitative difference. Now, imagine that I have some magic wand and I can change the energy ED. And I can push the level ED up. So then, okay, level ED pushes up, ED plus U also pushes up. And the next statement, which I think is less trivial, is that this ED plus U, the bare level, when it becomes high above the gap, becomes a resonance. However, what is left behind is a localized state that cannot escape the gap. So this localized state is still a discrete state. The composition of the state is different. It gradually becomes not a state localized at the magnetic atom, but it's a state composed from the quasi-particles of superconductor. But it's still in the gap, okay? And energy is, well, below the gap. So I'll try to motivate this result in perturbative treatment. So let's look now at the case when the empty level of atom is far above the Fermi level. So then hybridization just virtually occupies this level, but it's not really occupied. Okay, the electrons can virtually hop on and off and spend here time of order of 1 over u. I can exclude the states by what is called Schaefer-Wolf transformation, and that results in changing the description from hybridization to exchange interaction. Okay, so instead of considering the states in full glory, I confine my consideration to energies much smaller than U plus ED. And in this smaller space, I can replace Hamiltonian by the exchange interaction of the localized spin on the impurity with the itinerant spin. And the exchange constant J is proportional to the level width squared divided by the energy deficit. Okay, so this is a conventional picture of exchange interaction. Now, if we introduce superconductivity, it changes the nature of the itinerant states. So by doing Bogoliubov transformation, I can express the annihilation accretion operator of electron in terms of the superposition of the particles, right? Creation annihilation. The spectrum is different. So spectrum acquires a gap. So if I look at the density of states, it has square divergence at the gap. So that reminds a little bit 1D, right? So in 1D, for p squared over 2m, conventional electrons in one dimension also have square singularity at the bottom of the gap, at the bottom of the band, sorry. Now, to make this analogy even more detailed, I can express now this operator in terms of alpha and alpha dagger. Let's retain only terms that conserve the number of quasi-particles. Okay? Then, actually, this Hamiltonian is exact Fourier transformation of what would be in 1D a delta function potential. If you take Fourier component of delta function, it will have 1. So basically, what it means in momentum representation is that we have a quasi-particle momentum p, it scatters into p prime, and the amplitudes are all the same for any p prime. Okay? So it's just a constant time alpha dagger p, alpha p prime. Now, if I go back to this fake 1D representation, then the square root singularity corresponds to one-dimensional bottom of the band. And this one corresponds to a delta function potential, which is repulsive or attractive depending on the mutual orientation of the spins. So for the antiferrometric interaction and opposite signs of S and sigma, the potential, which is the counterpart of this term, is a well. Now, in 1D, we know that any well creates a localized state. So that's it. So basically, there is one-to-one correspondence between this state in the gap and the simple 1D quantum mechanical problem. So there were two important ingredients here. One ingredient I just discussed. This is the nature of spectrum that gives a square root singularity. Another one, which I kind of shoved under the rug, is that it's important that interaction is exchange rather than potential scattering. So if I'll do the same calculation for potential scattering and do it carefully, I will find out that the constant here actually is multiplied by some combination of UV factors, u squared minus v squared. And this combination vanishes at the bottom of the band. So it's important that we have the magnetic interaction. And for magnetic interaction, indeed, problem is mapped onto a potential that has non-zero, that basically is a well.
Leonid, I
Yes.
know why the spin flip terms are missing there.
Yeah, good, thanks. So the spin flip terms.
Yeah.
Yeah, so good. That's one more approximation that I did. I did consider spin as a classical variable.
Okay.
Okay, then I always can pick a basis. Now, it's a good question. So, I mean, if I want to claim quantitative rigor, I have to assume that spin is large. And then, as 1 over s, I can do this.
Okay.
Now, qualitatively, things do work, even for spin 1/2, as long as contact temperature is much smaller than delta.
Okay.
So things change when TK becomes order of delta.
Okay.
Okay, so that's a brief answer. But then I can give also references for this delta over TK physics, but it's different.
Okay, thanks.
Okay. Okay. So once again, from this analogy with 1D, I even can read off the the energy of the localized state. So measured from the gap edge, the localized state energy scales as as J squared. All right, so that's another representation of the same picture. So this is the density of states of a bare superconductor. Then if we introduce magnetic impurity, well, it does something to the density of states high above the gap where superconductivity is relevant anyway. And this state is the state in the gap produces some density of states delta function peak below the gap. Now, in terms of the composition of the wave function, as I said, for this level being high above the Fermi level, the contribution of the localized state to the the contribution of the wave function of the electron on the side or on the shell to the localized state is small. Okay, so this guy is represented only as J over Ed plus U, and the main contribution to the state comes from the quasi-particle states. So it's indeed hybridization that matters. So that's why I couldn't use from the very beginning the proximity effect. I had to get proximity effect from from considering the hybridization. Now, another important thing that comes from this fact is that the localization of the state, of the Shiba state, is actually kind of loose because, of course, everything decays eventually exponentially with psi of the host material. But on top of that, there is this factor, 1 over r factor, coming simply from the nature of S-wave state. Okay, so there is 1 over r decay of the Shiba state. It is, on one hand, it's fast. It's 1 over r. It's still decaying, but it has nothing to do with localization on the ion. It's a property of S-wave scattered wave in the host material. Pardon?
With elucidation?
Yeah, out of this come Friedel solutions. Yeah. Yeah. So what about the weight of the D level in the subgap state? So I already discussed it a little bit, but let's piece things together. So if gamma is small compared to delta, okay, and we have a level which is very close to the Fermi level, then as we discussed, the state in the gap is almost atomic state. So it's the representation of the wave function of the level of the magnetic ion, sorry, in the Shiba state is almost 1. So 1 minus gamma over delta. If I increase ED plus U, the representation becomes small, as we just discussed. And if I crank up gamma, then first of all, this the change of the Shiba state energy with upon the changing of ED plus U becomes more smooth. Okay, so it eventually goes almost to the gap, but at larger scales. But what happens with the representation of the D level wave function in the Shiba state? Actually, it was figured out long ago, and I learned it only after we did our work with Felix van Oppen group at Berlin, that actually there was a little not known to me paper before of Shiba as well in '73, where this was figured out. So basically, at arbitrary gamma over delta, the weight of the D level state in the Shiba state behaves as delta over gamma plus delta. So in particular, in a realistic case when gamma is large compared to delta, the representation of the D level in the Shiba state is always small. It's delta over gamma even if the level is close to the Fermi level. So it will be actually crucial for the explanation of the experiment, that the representation of the D level is always small. So the state that is forming a Shiba state is always almost constructed from the quasi-particle states. Okay, so not from the electron spends very little time on D atom, and mostly it spends time outside. It cannot go away because of the gap, but it's kind of hovering around the D atom, D level of the atom. Now, let me maybe quickly tell how the math can be done in a more rigorous way. So, in principle, all this physics can be obtained from what is called Bogleov-de Gennes equations, which is a Schrödinger equation for a quasi-particle in a superconductor. So, the wave function, unlike the simple quantum mechanics, the wave function is a column of 4 numbers, 2 numbers for spin up, spin down, and 2 numbers for particles and holes. So particle hole is called Nambu space, and well, spin up and down is conventional Pauli matrices. So it's a 4-component vector, and I can rearrange the Schrödinger equation in such a way that I sneaked out the one of the terms from the left-hand side to the right-hand side. So the potential, so to speak, which contains the psi function, I put it on the right-hand side. And now I can pretend to solve this equation by Fourier transform. So I can transform it. This guy is basically kinetic energy, and the Fourier transform of this guy is very simple because it's just a delta function in real space. So this way I find Fourier components of the wave function psi p in terms of the value of the wave function at r equals 0. So now I recall the definition of Fourier transform and write psi of 0 as integral d3p of psi p. So now if you plug in this into here, you'll get an equation which is eigenvalue equation, right? So it's psi 0 equals integral of something times psi 0. So it is eigenvalue equation, and it yields in principle some 4x4 matrix with kind of nasty kernel, but this equation contains information about all the energy eigenstates, continuum as well as discrete. And the discrete levels can be found quite readily. And here this expression for the Shiba states expressed in terms of the gap and the dimensionless exchange interaction. So what is left from the exchange is just this parameter gamma, which is density of states at the Fermi level times exchange constant times the spin of the impurity. So the states that correspond to the Shiba level, and there is, because everything is particle symmetric, so there is a particle-like and hole-like states, psi plus, psi minus, have quite simple construction. So now this solution that was basically in some different terms in Shiba's paper can be generalized onto the case of the chain. So this is somewhat new. And the idea is the same, that we put in the interaction with impurities to the right-hand side, pretend to solve the equation, find free components, and then plug it in back to the Fourier transformation, and that gives us the 4n by 4n matrix equation, right? So for each side of the chain, there are n sides. We have the expression of the wave function of a side at the side in terms of linear combination of the wave functions of all sides, this one and all other ones. So once again, this kernel contains all the information about the energy spectrum, and what one can do next is to look at the special case when the parameter gamma is tuned close to 1. And then Shiba states are deep. Okay, so then Shiba states are close to the Fermi level. In this case, we can single out the band of states close to the Fermi level that are mostly constructed from Shiba states and disregard the continuum. Okay, so we project all the states onto the states that are linear combinations of the Shiba states, but these Shiba states are adjusted so that for each ion, the direction of the quantization axis is the direction of the spin of this particular ion. So in particular, if you have a helix, then the states on the chain are adjusted in such a way that the spin up and spin down are with respect to the directional magnetic moment of each particular ion. And these directions are rotating in space with the pitch k sub h. Okay, so one thing that is important, that the Shiba states, as I said, decays 1 over r. So if we look at distances less than psi, and that's what I would like to do, so I look at distances much less than the host superconductor psi, we have quite slow decay. So this projection basically results in a sort of tight binding model where we have hopping matrix 2 by 2. Okay, and these diagonal elements HF correspond to hopping. Off-diagonal elements correspond to pairing. Now the hopping is not nearest neighbors. Actually, hopping is allowed between distant sides, and the hopping matrix element decays at 1 over x, where x is the distance between sides I and j. And similarly, the pairing term also couples in principle distant terms. Well, moreover, coupling at the same side is absent. As you can see, if I put xij equals 0 here, I'll get delta 0. And this is basically the p-waveness of the model. Well, moreover, you can see that actually the pairing matrix element is odd in coordinates. So that's typically p-wave pairing, as one can expect. Now, here's a hand-waving explanation why this term must be present in pairing. So basically, as we discussed in this toy model, there is a well for, say, spin down and a bump in potential for spin up. So there is only bound state, say, for spin down on every impurity, on every impurity. So now if I have two impurities that are have fermatic arrangement, then I can put electron with spin down here and electron with spin down here. But what the induced superconductivity is taking a Cooper pair, which is a singlet, and trying to shove it into the two sides on the chain. So if I have the ferromagnetic arrangement of spins on the chain, the overlap between this pair in the bulk and the pair that would end up on the chain is 0. I have to have some angle, which is given by this pitch. So as long as the states on the chain are not exactly triplet, I can project the singlet of the Cooper pair onto the states of the chain. So, and that basically is given by this factor sign. So now, yep.
You don't have any spin orbit here in your model?
Yes, thanks. Thank you. So just one line before. Here I have no spin orbit. I have helical arrangement. So now, as we discussed, at least on the simple level, one can map between two problems. One without spin orbit but with helical field, and another with spin orbit and without helix. Okay, so it is studied in a bit more detail actually in a later paper of Bernevik's group, and I will not discuss it in detail, but basically there is a translation between the helix angle and spin orbit interaction constant. I can introduce something like spin orbit angle, which plays the same role as this pitch KH.
But in your calculation, I mean, this is the outcome of your calculation in your model, right?
Yes, absolutely. Yeah.
Wave as an outcome, and you are not. So you are assuming that you have a ferromagnetic chain, right? Or
so in this calculation, actually, if you wish, I cheated. So in this calculation, there was a helical chain and no spin orbit.
okay, good.
Okay.
That's what
And I have to admit that through the rest of the talk, I'll stick to this model.
Okay.
But in the subliminal messages, it doesn't matter. Okay. So,
okay, I understand.
but there is no, at least we didn't do the calculation for ferromagnetic order and spin orbit. All we did was this model. Technically, it's simpler. So.
That's fine.
So KH is imposed by you by hand?
Yes.
KH
is imposed by hand. It has nothing to do with KF. Moreover, it is in small KH compared to KF. That's true, yeah, thanks. Yes, KH is imposed by hand. As just I try to answer, there is a correspondence between the dimensionless parameter KHA. A is the distance between the magnetic impurities, and spin orbit angle. And typically, spin orbit angle is relatively small. Okay, so it's not 1. So, and this is a translation that I will use kind of all the time, and I will think of alpha, which is moderately small. So now let's make some simple estimate. So here is this Hoppeck matrix element, okay? And what I would like to emphasize that the magnitude of the Hoppeck matrix element actually is proportional to the gap in superconductor, delta. Okay, so it's delta in lead. Okay. Hoppeck matrix elements decay as 1 over x. And let's put as a typical x just distance between the nearest neighbors, which is a, right? So then the estimate for the bandwidth, Hoppeck bandwidth, will be delta over kfa. Okay? So it's step number 1. Step number 2. We look at the characteristic velocity. So for that, I'll take the bandwidth and the Brillouin vector, which is 1 over a. Combine to get velocity. So I'll divide by ws by the Brillouin vector, which means that I multiply ws by a, and get delta over kf as an estimate for the typical velocity in the band. So again, notice it is not firm velocity in the host material. It's delta over kf. Now let's look at the pairing interaction. Again, it's proportional to delta. And if I replace this x by a, it's inversely proportional to kfa. So delta over kfa times this sine of the pitch, which I replaced already by alpha. We're almost done. So to estimate psi, I just divide v by delta. And what I'll get is something where delta cancels out. So as a result, you see that this induced, the coherence length in the induced band actually doesn't know about the gap in superconductor. It knows about the distance between atoms in the chain and the spin orbit angle. So basically, this is the explanation. Okay, we will we kind of make it, we'll glorify a little bit further, but this is the main thing. So if alpha is small, then basically I can replace it by A over alpha SO. Okay, so now, well, after all, it's a relatively simple Hamiltonian, so one can do Fourier transform and study the spectrum in all glory details. And here's the result. So this long-range hopping actually leads to some strange spectrum consisting of straight lines. Okay, so basically, it's Fourier transform of 1 over x is logarithm imaginary part is some step. So basically, that gives some strange dispersion relation. And depending on the position of the of the single ion Shiba level, we either in the trivial state, and the trivial state correspond basically to the Shiba states are when they're above the Fermi level, and this band doesn't take in electrons. Now, if we reduce the Shiba state closer to the Fermi level, the band takes in electrons, and then this is this non-trivial topological state, which is a p-wave superconductor. Now, depending on whether the Shiba state is above or below the Fermi level, so this gamma is less than 1 and larger than 1, there are two states that are differing by topological index. Again, it's a secondary, not very important thing. Now, depending on the relation between Kf and the pitch, there is topological state or non-topological state. So once again, if we make pitch large, then we are getting to non-topological state again. So that's why we are interested in Kh actually small. So again, it is interesting, but secondary, I will skip that. Now, as a topological index, just for information. So how this can be calculated? So as I said, the state of a quasi-particle in the one-dimensional band is a spinor in the Nambu space, in particle Hall space, and I can form a vector out of the two components of the Hamiltonian for a single quasi-particle, and this vector rotates as a function of momentum. So there is one-dimensional Brillouin zone. This vector formed of h and delta depend on the point in the Brillouin zone, and I can look how it rotates around 0 when I go from one side of the Brillouin zone to another side. And it can do something trivial, meaning without going around 0. And this is top index 0, it's trivial topological state. Or it can go around, if you look carefully, actually here it goes around the 0, around 0, and this is non-trivial state, and it can go clockwise and counterclockwise, and this is plus or minus 1, and that corresponds to this part of the diagram. Now, if we are in the topological state, then actually there is a Shiba state, a localized state, Majorana state at the end of the chain. Again, having this two-dimensional, well, having this tight binding Hamiltonian, we could find the state explicitly. And moreover, asymptotics of the wave function of the state can be found analytically. And actually, it looks not so good, because actually the Majorana state decays pretty slowly with the distance as 1 over x log squared x. And this is the result of this very slow decay of the matrix elements. So if the happy matrix elements decay slowly, there is no chance to get a strong localized state, right? So that looks not so good. But actually, it turns out that this analytical asymptotic works only at fairly large distances from the site, from the end of the chain. And the numerical solution shows that there is a strong decay, exponential decay, close to the edge of the chain. And this decay indeed fits quite well, this slope, to this naive consideration of the effective coherence length, which is basically the inter-atomic distance divided by the spin orbit angle. And only then there is a slow decay that you cannot even see here the decay. It's this function. But it's after the wave function dropped already by 2 orders of magnitude. So basically, for practical purposes, indeed, there is strong localization, and then a long tail of the wave function that doesn't decay much. So that doesn't decay fast, but it's only a small tail. So that's basically the picture for a chain of Shiba states where atoms are far away from each other, and there is no direct hops between the atoms. Now, the drawback of this model is actually we had to assume some fine tuning. So we had to assume that this Shiba band, which is delta over KFA, is somehow tuned to the Fermi level so that there are electrons in this band. And that requires the fine tuning to the tune of MEV, whereas it requires very fine tuning of gamma to 1. Now, the thing that in experiment actually the iron atoms are quite close to each other, and that introduces the following ramification. So basically, instead of just separate d levels, there is a chain of levels, and they may form a band, and the width of the band has width of order of 1 eV, well, roughly. So if this level is not too high, then this band will overlap with the Fermi level, and then the bottom of the band will be filled by electrons. So having wide band actually is good because we can have non-trivial state even without fine-tuning of the Shiba states to the Fermi level. So now we need not so fine-tuning on EV scale rather than MEV scale. Now, again, as I said, I will not consider the fermiotic arrangement and spin orbit, but instead I'll tell that it's the same as having no spin orbit and twisted spins. And what I'll do now is I'll do just estimates and then tell maybe in the last few minutes how the calculation is done. So what is the difference? If you have just overlapping localized states, there are hubs between the states, and the bandwidths, and at least some bandwidths of the d-level states, which I call W. Now, the bare velocity for the band of overlapping these states is W times the distance between the magnetic ions, so A times W. But now what's important actually is that the electron spends little time on the d atom. As we discussed, for the Shiba state, the representation of the d state wave function is proportional to delta over gamma. And it's small if delta is small. So basically there is a wide band, but electron spends very little time in this band. It's mostly spending time outside. And that reduces the Happing matrix element for the Happing atom frequency basically for the electron. And as a result, the effective velocity is reduced by this parameter delta over gamma. So on the formal level, it corresponds to the large self-energy for the electron green function. And the part of this that is large actually is the omega-dependent part. So if you just look at at something which is similar to mass renormalization in conventional Fermi liquid theory, that's what brings this factor into the Fermi velocity. But on the hand-waving level, basically, this reliance is the explanation. So once again, so we assume here that the main hubs correspond to direct hubs between the irons, and we neglect the process that we discussed before through the superconductor. So still for these direct hubs, there is suppression due to the small presence of electron on the chain. Now, with induced superconductivity, it's the same consideration that we had before. It is the induced gap is proportional to delta times the spin orbit angle. So now we just combine these three lines. Okay, so we have the renormalized VF suppressed by factor delta over gamma, so it's proportional to delta. The induced gap is also proportional to delta. We take the ratio, and we get induced psi proportional to the distance between atoms, 1 over spin orbit angle. And then this ratio is basically the atomic properties of the chain. It's the bandwidth of d levels divided by the width of separate levels with respect to leaking of electron into the host matrix. Okay. Now this estimate fits well with what we had before. If I put W over gamma order of 1, then we are back to the formula that we had before. Okay, so if this is a parameter order of 1, then we get A over alpha SO again. So these two estimates match each other. So the outcome again is that the coherence length in the 1D induced P-wave superconductor is independent of the gap in the host material. It knows about the atomic properties of the chain. Now, how it's done in terms of math. So we use as a starting point this Shiba paper that I mentioned in 1973, that paper actually redid Anderson impurity consideration with mean field self-consistency for the superconductor. So we do a similar thing. We start with the Hubbard model with on-site repulsion, treat the on-site repulsion terms in the mean field, then introduce tunneling or hybridization between the d levels and the itinerant electrons, and form the equation for the green function of electron that now has actually 8 components, because there are quasi-particles in the bulk, but there is also state on the d level. So this wave function that form G is the column of eight numbers, not very pleasant, but one then can exclude d levels and project this way or reduce the problem to the foreign by foreign matrix as we had before. And then further, if we look at the sub-gap states, we project the states onto the single spin direction for each of the sides, and that reduces further foreign by foreign to 2n by 2n matrix. And then we have just the 2n by 2n problem, and we do Fourier transform and find the dispersion relation for the band. So it looks a bit nasty, but actually I just tell that which term corresponds to which part of the hand waving discussion. So this first term is basically the dispersion relation for the tight binding hopping along the wire. You see this characteristic cosine, and KH here is just due to the either helical arrangement or spin orbit pitch. Now, the next term is this non-local hops through the bulk, which I had in the first part of the discussion when we didn't have direct hopping, but only hopping through the bulk. So the spectral normalization comes out of this term that also is a term that corresponds to hybridization of states on the d levels with states in the superconductor. And finally, this last term corresponds to the induced p-wave gap. So these are all the ingredients, and basically this equation, okay, it's simple, but it can be solved numerically. And that gives excitations spectrum epsilon of k. It gives density of states, and also if I look at the equation in real space with the end at some point, say at x equals 0, I can look at the end states, localized states, Majorana states in this model. So here are the results. So first of all, if you remember this diagram that I had before with two signs of topological index, it remains roughly the same. So there are two types of topological states. The coordinates here is the depth of the Shiba state. As I told, it cannot be larger than 1. Okay, so ES over delta is up to 1, and this axis is the width of the band of d levels in units of delta. So this is huge usually. Okay, so we have some order of 100 ratio of W over delta, and there is a part of two top indices for the non-trivial state. So if we are somewhere inside the non-trivial state, there is a gap which is of p-wave type, and we can recognize elements of the discussion I had before in the spectrum of quasi-particles in the one-dimensional band. So this flattening of the band at large k corresponds to the fact that the level cannot escape the gap. Now there are some peculiarities in the spectrum, and that comes from the hops through the superconductor, long-range hops that lead to non-analytical structure of the dispersion relation. So that gives some additional van Hove singularities in the structure of density of states. And finally, the gap is produced by the spin orbit interaction and or helical structure and the gap in the host material. So this is small compared to delta, proportionally to alpha, proportional to the angle. So out of the spectrum, one can find density of states. So the blue line here corresponds to somewhere in the middle of the chain. And as you see, there are lots of wiggles. This comes from this unusual spectrum, flat parts. But there are also strong Van Hoff singularities at the edges of the gap coming from the flattening of the spectrum. And the red one corresponds to the end state. This peak is broadened artificially. It should be delta function. And it's coming from the Majorana state. So we used, I mean, the numbers that we used are not, well, okay, I'm not sure how reliable are they, but we just used what was published in the experimental paper. And if you use these numbers, it looks like the decay of the Majorana state is about 4 times the inter-iron spacing. And once again, as you see here, there is a tail here, which is this 1 over x log squared. But it happens only when the wave function already died out by a factor of a million. So basically, you can hardly see this, and the only thing that we think is seen is this part. So basically, this is the main part of what I wanted to tell. I think I'm slightly beyond the time. I'll spend another maybe 90 seconds on another advertisement. So this is all for density of states is a nice thing, but how you measure it. So one can tunnel with normal STM, but our chairman actually uses some more sophisticated tool, which is superconducting tip. And what is good about superconductivity is that it gives a sharp density of states, as I already mentioned. And here's just some graph from some oldish PhD thesis from cyclic group. It's really very sharp peaks. So one can do the following thing. That basically you want to scan this level somewhere in the middle of the gap. So it's nice to have a tip that has a sharp density of states as well. So then when you scan, you see strong features not in derivatives, but in currents itself, right? So not di dv, but in I. So this is an advantage. And what we looked recently with a group of Felix von Oppen was the prediction of the conductance one would find for Majorana state. And it has some universality. So the shape, the shape of the conductance peak has kind of a step-like form, and the step is proportional to square root of h with some non-trivial coefficient. The width of the peak is also has non-trivial scaling with the tunneling rate between the tip and the substrate. So I will stop at that, and you can read it in more detail, and just conclude telling that there's the main message here is that basically the localization of the Majorana state at the end of the Shiba chain may be independent of the Xi in the host material. And the second thing is that actually it would be nice to repeat these experiments with superconducting tip because you have much more resolution. So thank you.